So in this lesson, we're going to look at the second application of centripetal forces that I like to use as a common application. And this is looking at forces on curves on highways. So when you're traveling around a highway curve, what actually keeps your vehicle on the road is a centripetal force. If we think about it as you curve to the right, there must be a force toward the center of the circle which allows your car to curve to the right. And there are two main forces that are responsible for this. In the vast majority of driving conditions you would deal with, friction is partially responsible for this. And you might say, well, wait a second. Friction always acts in the opposite direction of motion. How can friction be in the direction I'm moving? Hold that in your head for a second. When we get to talking about friction, we'll explain why that is. So this would be one of the weird exceptions to the rule that friction always acts in the direction, in an opposite direction to what you're moving. In this case, friction acts toward the center of the circle in the direction your object's motion is changing, which would seem really weird to me. The second example is the normal force. And this is acting in most curves that you would deal with on a highway. In fact, most curves here in Minnesota, you'd have the normal force acting on them. These are what we call banked curves. When I talk about a banked curve, I mean the outside edge of the curve is at a higher height than the inside edge of the curve. And so the normal force is also helping to push you around the curve as well. We'll talk about some reasons why we bank curves when we get to that in a minute, and some reasons why we might want to use friction as an example of why we move around the curve. Depending upon the type of curve and the conditions, we might be using one force or the other force, or both forces. So let's look at what would happen if we had an unbanked curve or flat curve. What's keeping you on the curve or allowing your car to move around the curve is the static frictional force. Now, you might think that makes no sense for a couple of reasons. The first reason I already pointed out, that doesn't friction act opposite the direction the car moves? Then how can it be acting, in this case, perpendicular to the car's motion? That doesn't make much sense. And the car's moving. How can it be static friction? Doesn't static friction deal with objects that are not moving? Well, wait a second, and I'll explain both those. The first one of those, how does static frictional force, or how does frictional force act toward the center of the curve if it should be acting opposite the direction of moving? Well, think about this. What direction would the car move if that frictional force didn't exist, regardless of what you did? Well, it would keep moving straight. Well, if it's curving, and we know that what's allowing you to turn in this curve is the force of friction, because that's how your car actually turns, well, then that force must be acting toward the center of the circle. So really what that frictional force is really doing is opposing the impending motion of just flying straight ahead off the curve. So it does work as, well, opposite the direction of motion, because if it didn't exist, you're going to keep moving in a straight direction. It's going to move in a direction that's off the curve. Now, how is it static frictional force? Why isn't it kinetic frictional force when the tires are clearly moving when your car is moving? What I would challenge you to do is think about a tire moving and put a dot on the tire and think about how that dot moves with respect to the road surface when it's in contact with the road surface. Well, it really is in contact with one point and then it keeps moving, or it just keeps rolling. It doesn't slide across the road surface. So it is static frictional force. If we think about how that dot moves with respect to the road surface, it isn't sliding along the road surface, which would be kinetic friction. It is actually stationary for that moment in time with respect to the road surface. So it's actually static friction that keeps your car in a curve. In reality, it's static friction that allows your car to go around curves. It allows your car to speed up and allows your car to slow down. Once static friction once you overcome static friction and your wheels start to slide along the surface, we're then dealing with kinetic friction, then you run into really three problems. You can't speed your car up, you can't slow your car down, and you can't turn your car. Now, it's worth pointing out if your car is moving too fast, you will slide off the curve, and so we can actually predict what the maximum speed is. Now, it's worth pointing out for the unbanked flat curve with static friction, you could be traveling anything less than the maximum speed, and so let's actually calculate the maximum speed in two different conditions. We're moving around the curve of radius 50 meters in dry weather, and I actually looked up what the coefficient of static friction for standard tires is in dry weather, kind of ideal weather conditions, and it's about 0.95, and also looked it up in icy weather conditions if you have a sheet of ice over the road, and it's 0.10. So we're going to calculate the maximum speed in both these cases. So first thing I'm going to do is draw a free body diagram. I have the weight acting downward, the normal force acting upward, and my frictional force acting toward the center of the circle. Now I know the centripetal force and the frictional force have to be the same thing. So I could say mv squared over r is equal to the frictional force. Well, I know what r is, and I'm trying to find v, so hopefully m gets canceled out. I know I can calculate the maximum frictional force. That should be the coefficient of friction times the normal force. I can calculate the normal force because sum of forces in the vertical direction should be 0, mg. I can plug that into my equation, substitute that in for the frictional force, and guess what? Something beautiful happens. The mass of my car cancels out. I can multiply by r, and I have an equation which relates the speed that you can travel around the curve to the coefficient of friction to the radius of the curve. So really only two things will determine what your maximum speed is: how large the curve is and what the road conditions are, mu s. And so we can calculate that maximum speed by doing mu s gr, the square root of that. Now, do you ever need to know how to derive this equation? I probably would never ask you to derive this equation. It might be kind of cool to have it in the back of your head how this gets derived, but I definitely would know what this maximum velocity equation is for a flat curve dealing with static friction. So I can plug in my two values and find that under ideal conditions, it's 26.1 meters per second, and under icy conditions, it's 7 meters per second. So when we talk about in icy conditions to lower your speed, this would be one reason why. If you have really terrible road conditions, the speed at which you overcome that frictional force becomes much, much, much smaller. This would be true if you're trying to slow down in icy conditions too, that you can't brake as fast because, well, the force that you can apply that allows you to continue to move in the circle is smaller. So there's your equation for your what I would call a flat curve with static friction. Now, what if we looked at a bank curve? And what if we looked at the worst possible conditions we can ever imagine for a roadway? We can get around this curve another way. So if we have an icy curve and we have the worst tires imaginable, and we maybe put oil on the icy curve to make it even more slippery, even less friction, and so we've basically reduced the frictional force to 0, there is still a way you can get around the banked curve. This type of curve is actually very common. In fact, the vast majority of highway curves built on roads in Minnesota are banked curves, and the reason for that is, well, about 6 months out of the year we could have not so good driving conditions. It's possible to get ice and snow and all sorts of stuff which reduce the static frictional force between your tires and the road surface. And this is another way to allow your vehicle to travel around a curve in not ideal conditions. This also happens to be how an airplane turns. If you've ever been on an airplane, you notice that when it turns, the wings on the outside of the turn lift up and the wings on the inside of the turn go down, and so it's actually the lift force, which you can think of as a force perpendicular to the wings of the airplane, that allows the airplane to make that curve. So let's look at this problem and say we have a car that's going to travel around a curve at 250 meters and there's absolutely no friction, the worst possible conditions you can ever put at, and it's banked at an angle of 15 degrees. So let's do a free body diagram of the weight downward. I don't know why I put a white arrow there, but I did. That's really hard to see. Normal force upward, And the centripetal force is actually in that direction. I've used this as a dashed line because remember that the centripetal force is really the net force acting on the system, not really a new or an additional force that's acting on the system. That's one thing that sometimes trips people up, is that think of centripetal force as the net force that you do F equals ma for, not a new force that we just came up with to add to the system. So in reality, we'd say let's make the x component horizontal in the direction of the centripetal force. So left is the positive x direction. That would make up and down the y direction. And so the force that I'm going to break up into components in this case is the normal force. That the x component of the normal force keeps you moving in the circle, and the y component of the normal force is equal to your weight. This would be an example of a situation where the normal force is actually greater than the weight of your object. And it has to be in order for you to move in a circle. So let's actually work through the math here. I would need to figure out the components of the normal force. I could do that. It's worth pointing out that that angle should be the same angle as the 15 degrees. You can take some time yourself and prove that out geometrically. And so the x component would be n times the sine of the angle, the y component n times the cosine of the angle. It's worth pointing out the way we would do this. For the block sitting on the ramp before, x would still be n sine of theta, y n cosine of theta. So I can solve for the normal force using the equation on the right. That normal force times cosine of theta equals m times g. So the normal force is m times g times cosine of theta. Let's take and substitute that in for normal force over here. I get mg sine of theta divided by cosine of theta. A couple things happen here. The m's cancel out, and I can also simplify sine over cosine. For those of you who are really good with trig, you might remember the trig identity that sine divided by cosine is tangent. If you don't remember that, you can actually do that fairly quickly to prove that for yourself. The sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. If you divide those two ratios out, you get opposite over adjacent, which is tangent. If we multiply by r, there we go, we get our answer that v squared is g times r times tangent of theta, where theta is the angle that your curve is banked. So we can calculate out that speed, and it's 25.6 meters per second. Now it's worth pointing out for the banked curve without friction that this is the one and only speed that you can travel around this curve at. So if you happen to have that absolutely horrible road condition that you'd never want to have, there'd be one and only one speed you can get around the curve at. Well, quick aside, I have some story time for you. Mr. Inman has actually done this in a car. Gone around a banked curve at the one and only one speed in absolutely horrible road conditions. And this occurred when my daughter Julie was about 6 months old. I was driving home for Thanksgiving. My parents live in southern Iowa. And the road conditions were, I would say, not ideal, but probably in reality, the road conditions were absolutely awful. For those of you who have ever driven south on Interstate 35, probably takes you somewhere between, 3.5 hours, 3 hours to get to Des Moines. On this day, it took me 6 hours to get to Des Moines. It was that bad. Well, anyway, we're going off on an exit ramp, and it's one of those exit ramps that curves around in a circle to get off to go to the bathroom and get some snacks. And you maybe have noticed on those exit ramps, there's a sign that says something like speed 30 miles per hour or something like that, or ramp 30 miles per hour. If you ever come into Faribault from the north from Minneapolis and turn off by the truck stop up there on the far north exit into town, when you drive by the Grand Stay, you'd see that sign there because it's exactly one of those. Well, as I came around that corner, I slowed down to about what that speed was. It was like 30 miles an hour, whatever it was. And so I was traveling at about exactly 35 miles an hour. And as I start to turn the corner, I made the critical error of hitting the brakes. Newsflash for you, if you hit the brakes and you're driving on ice, your car will slide. And that's what happened. My car started to slide. But what my car did was start to slide in a circle going around this exit ramp. How it slid in a circle, I don't really know, but it did. And the end result was we ended up traveling in a circle. We did almost an exact 360 down the exit ramp, and I ended up toward the bottom of the exit ramp, pointing in the direction that I wanted to travel when my car actually came to a stop. Now, I'll tell you what I did driving the vehicle when this happened. I took my feet off the brakes and the gas. I might have even let go of the steering wheel at that point, because at that moment that you start to slide on the ice, you are not in control at all. You're going to go to wherever the car wants you to go at that moment. My younger brother was actually sitting in the passenger seat, and his response was, some word I'm not going to say right now, did that really happen? And yes, the answer to that is yes. Now, the reality in most cases, you're dealing with both the frictional force and this banked curve force, but we can do either or separately. Sorry for the little story time lesson. That made me a little bit longer, but it is kind of a quick example of where we could use that idea of a banked curve.